didn't make it up.
Well, I didn't hear it. That's what it sounds right.
Everybody
It sounds-
It sounds.
It is.
Mara Raquel Pedersen. Mara Raquel Pedersen.
No, absolutely not. I would change it. Not that
I
there's
was
anything
supposed to
wrong.
be Ella Grace.
Okay.
Just like Ella.
So, are you measuring your pH?
Yeah, but it's so wrong.
Why?
Well, it's still going up, but it's at 5.79.
Or was this made in China?
They lied it up.
They didn't buy Amazon. I don't know.
It's not working.
Okay, I don't know.
This must be an American one.
Okay, so here's what we've got. We're going to begin to look at how you determine what's called the rate function, how you describe how fast the reaction takes place. So let's just start with question number 2 out of chapter 14. So you're given this graph. If nothing else, look at this in terms of like, okay, what units are you going to have? Well, anytime you have something in square brackets, what's that measured?
Concentration.
Yeah, measured in
Polarity.
molarity. Okay? So this is molarity, this is time typically going to be in seconds. So if it was a linear function, which it's not, it's a quadratic, technically it's a square function, then if you were to look at the slope of the line, you would have units of molarity per second. So this is going to be one of the recurring and important ideas you need to get out of today. Any rate, unless you're told something differently, is always going to be molarity per second. Now, sometimes they'll get cute and change this up a little bit. I just don't want you to freak out if you see this. Because molarity is, what's another way to express molarity?
Most liter.
Moles per liter. So you could also write this as moles per liter seconds. Okay? Sometimes they'll even get fancier and they'll go moles to the moles and then liters to the -1, seconds to the -1. Okay? I'm just telling you, if you see it, don't flip out. They might even show this as molarity seconds to the -1. Okay? So I just point this out because different books express this differently. But here's the main point of the story. Any rate function is going to be the change in concentration per unit of time, and typically it's molarity per second. So if you look at the reaction that I did yesterday with the silver nitrate, and I dropped in a piece of copper. So this could be the concentration of the copper ions as a function of time, because we put in, if you look at this reaction, we put silver ions and elemental copper, and that produced Cu2 plus elemental silver. We balance that out, we put a 2, we put a 2, okay? So over the period of time, this could be the concentration of the copper ions. So initially, those copper ions would start to form very quickly as that single displacement reaction took place. So if you look at this from yesterday, the copper ion solution hasn't changed. Okay? We know that the cool part about this reaction is that we can visually see it. We can see that it's producing copper ions, and we can look at that and go, okay, hey, it's turning blue because that's the color of copper ions. This wouldn't work with something that doesn't have a distinctive color to it, but this one we can visually see it. Oh yeah, right, concentration is going to go up. So over the period of time, if you let the graph go long enough, it would just become a horizontal line. Now, what's not on here, what would happen to the concentration of the silver ions as a function of time? Yeah, it would start up high, and then it would go down. It might go to 0, it might go to some value, but it's going to go down. So these two values are going to cross at some point. Okay. So on number 2, you should have equal numbers of true statements and equal numbers of false statements. Okay? Just saying. When you get to question 17, and there's a subtle part, this is still out of chapter 14. On question 17, it's got what is meant by the term reaction rate. here's what is important about this, because it's a rate function, okay? It isn't the change in concentrations, that's part of it, but it's the change in concentrations per unit of time, because it's a rate function, okay? So you have to put the per unit of time on the end of that statement, because it isn't just how fast it changes. It was just like, if I asked you how fast are you going, and you just say 40 miles. Okay, great. You told me how far you went, but I don't know how long it took for you to go there. Okay, so that would be the same thing. If you just tell me, oh, it's just a change in concentration, that would be like you telling me I drove 40 miles. That's not enough information because it's not a rate function. Okay. When you get to question 18, this is what we just talked about. What are the units used to express the rate of reactions occurring in a solution? Okay. Again, you can put molarity per second, you can put moles per liter second, you can get fancy if you're into negative ones, you can express it that way. I don't care. Really doesn't make any difference. When you get to chapter 15, and question 15 out of chapter 15. So what's going to be important there is you realize what you have to worry about and what you don't. So on 15 it says just write the KC for the following. Okay. Now the unique thing about it, even if you look on 15A, because of the fact that those are gases, you can still talk about that as a concentration, but it's just moles per liter. So if you were to have, hey, you have a certain size container and you know how many moles of gas are in it, you can talk about that in terms of moles per liter, just like you could talk about, hey, here's the concentration of salt. It's a 1 molar solution. Oh, I put 1 mole of sodium chloride per 1 liter. So it still works the same way, but it's just not a solution, but it's still the same quantity of moles in a certain volume. So that's how that works. Now, what you have to watch for is that there's a couple of things. On 15, out of chapter 15, I want the expression, and then you also have to tell me if it's homogeneous or heterogeneous. So make sure that you have indicated both of those on question 15. Now, what you have to watch is one like on 15E, because that's a redox reaction. You took a piece of silver, dropped it into a solution of like zinc nitrate. You're going to plate out the zinc, and you're going to make silver ion. When you write that expression for KC, don't worry about anything that's solid. Like, don't put in that silver. Don't put in the zinc, because of the fact that you can't talk about the concentration of a solid substance. You can only talk about the concentration of ions, or you can talk about the concentration of gases. Okay? So make sure, like on that one, you don't have the silver and the zinc on that one. Now, let's talk about 18. Following reactions lie to the right, favoring formation, and which lies to the left, favoring, so this one on this one. So on 18, here's the general idea. The bigger the K value is, and this is true of everything that we've talked about, Ka, Kb, Ksp. Big numbers, small numbers. Small numbers, which means the forward reaction is not favored. Okay? Whether it's the dissociation of a weak acid, whether it's a solid substance dissolving in water, anything that has a very small K, less than 1, is not favored in the forward direction. So that's the only thing you can do on 1518. So, okay, if you look on that one, with that first one, you have nitrogen combining with oxygen to produce nitrogen monoxide. That K value on 18. So that K value on 18A is a really, really big number. Okay? So that means the only way that you can get a really big number mathematically, if you look at how you calculate Kp, in this situation, that would be that NO2 concentration squared divided by your no concentration squared, and concentration of your oxygen gas. So mathematically, the only way you can produce a big K value is if you have, and it's always, there's no exceptions to this rule, it's always products over reactants. Always. There's no exception. So the only way that I can make a big Kp value mathematically is if I have a lot of product and a little bit of reactant. That's the only way I can make a big Kp value. Now, in contrast to that one, when you get to 18b, you have a really, really, really small K value. The only way you can have a really small K value is if the products are a small number and the reactants are really, really big. Okay? So if all you're given is the K value, that's how you can determine, well, which way is it going to go. Hey, if it's a big K value, you're going to favor products. If it's a small K value, you're going to favor reactants. Okay, which is something that we talk about in any number of situations. Now, here's the heart and soul of this. When you get to 21 and 22, so Kc and Kp are similar type calculations. The only difference is the one is based upon concentrations, one is based upon pressures. Okay? And there's this conversion, and if you ever need this equation, don't memorize it. I will always give you this equation if you need it. But what that allows you to do is basically it's a bridge that allows you to talk about K values in terms of pressures and K values in terms of concentrations. And here's why we need that. Because if you look at what you can physically measure, especially with gases, it's difficult to measure concentrations of gases. And mainly because of the fact that you would have to know the number of moles in there per liter. That's tough to do. It's like, hey, Burkham, do you have like a mole sensor? And it was like, don't have that, okay? But we have pressure sensors, okay? So if we can measure the pressure, which is easy to do because y'all work with pressure sensors before. Okay, right, okay? So like here's a simple pressure sensor. So right now it's at, some number of hectopascals. So if I screw this down, okay, and decrease that volume, you can see that that pressure goes up. So in this situation, it's really, really easy for me to measure the pressure. Oh, I hook it up to a gauge. I don't have a gauge that's going to measure moles per liter, but I can measure pressure pretty easily. And that's just what allows you to cross over that bridge between concentrations and pressure. That's why it's handy to have that equation. So the answer to 22 should be between 8 and 900. Okay? Just to give you kind of a ballpark. Now, when you get to 42, okay, and here's one of the most important things you've got to get, and 42 and 43 are both two sides of the same coin. So on 42, here's what you've got. You have some generic reaction of A as a gas, B as a gas, turning into some new product, C as a gas. Okay? Everything's in the gaseous phase. One of the things you have to figure out is your value of delta N. You don't have to have that, but I just want you to make sure everybody's cool with how you get delta N. So delta N is the moles of gas, okay, not liquids, not solids, only gases. So this has 1 mole of a gaseous product. You have a total of 2 moles of gaseous reactant. So if I take 1 minus 2, delta N in this problem would be -1. You don't need that. I just want to make sure everybody's cool with how you get delta N. Now, what's happening on 42 is that you get this reaction and that they tell you that Kc has a value of 2. Okay? So what that means is that this reaction is kind of favored in the forward direction, but it's kind of a wash. Okay? It's kind of favored. This isn't where this would indicate this reaction like bam, going to happen. It's like, is it favored? Yeah. But it's kind of like, You want to go to prom? Yeah, but we're just friends. Okay? So this is not a full lifetime commitment. Hey, let's go to prom. We're just friends. We'll go, but hey, we're really not that excited about it. So here's what's important in terms of how you calculate this value. Okay? So with this, write this down. You get, okay, great. If you look at how they calculated that value of K, that was the concentration of C divided by the concentration of A times the concentration of B. It's always products over reactants. This is simple. Nothing is going to get cubed. Nothing is squared. Nothing is cubed. There's no coefficients in front of it. This is as simple as it gets. Okay? Now, on 42A, what you're told is that everything has a concentration of 1. Even though this is a gas, we're going to still express this in terms of molarity. So this means in this container, what would happen, physically take place, is that in this, what they're saying is that initially you're going to have in here like 1 mole per liter of gas A, 1 mole per liter of gas B, and out of this, you're going, when you get done, C is going to have a concentration of 1 mole per liter. Now, that's tough to do, to physically measure, mainly because of the fact that you've got all 3 gases in the same container. So, and you have this pressure, and it's like, okay, the pressure is so many, like for example, this is just air inside this vessel. Okay, well, the total pressure is, 1,000 and whatever. Well, how do you determine how much of that pressure is coming from the nitrogen? How do you determine how much of that is coming from the oxygen? So this works as a great kind of mathematical model, but physically this would be tough to measure. So here's the point of 42A. Everything has a value of 1. So that means Q is like a snapshot. Q is going, okay, let's get a pulse for what's happening. Okay, are we in equilibrium? Are we not equilibrium? Okay. So if you plug in the numbers, obviously you get 1. So at this point on 42A, Q is less than K. Mother Nature is not happy at this point. Mother Nature's going, no bueno. Okay? This is bad. I'm not happy. Okay? I have a problem with this because I'm not in equilibrium. So Mother Nature is going to go, I got to change this because I can get back in equilibrium because I want to sit there and go back to hitting my hookah pipe and showing out. I want to deal with this situation. I want to get back to being in equilibrium. So mathematically, we need to make this bigger. Okay? Because right now, everything is at 1, and Mother Nature is going, great, I'm happy that you all are at 1. I'm not. Good for you all. I'm not pleased. So the only way that you can increase this from 1 to 2 is mathematically, what are you going to have to do with the concentration of C? C's got to get bigger, and then at that same time, you're going to drop the concentrations of A and B. Okay? So in this situation, since Q is less than K, Mother Nature goes, man, I got to make more product. Okay? It's the only way this is going to happen. So in terms of how you express this, there's 2 ways that you can do this. You can say, hey, we're going to make more product. Okay? That's an option. Or you could say the equilibrium is going to shift to the right. Okay? What you got? So you can either say I want to make more product, or it's going to shift to the right. Now, in contrast to this, you get to C. If you plug in the numbers on 42C, Q is going to equal 4, which is too big. Mother Nature's going, oh, this is not good either, man. We went too far. We've made too much product. So now, because of the fact that Q is now bigger than K, the only option that you have then is to make C smaller and make A and C get bigger. So then you can say either it's going to shift to make more reactants, or you can say it shifts to the left. I don't care. Pick one. Okay? Now, On 43 especially, if all you put is left or right and I don't see any calculations of Q, I'm going to be very skeptical that you actually did that and you actually understand what is happening. Because those Q value calculations are a little bit complicated. And I find it hard to believe you're just going to look at it and go, oh, it's going to shift to the left. I can just look at it and tell. I don't need to calculate Q. No. Okay? You show me that calculation of Q on, especially like at 42, that's simple. Those are small numbers. But 43, I want to see what that Q value actually is, because that's the only way I'm going to believe that you know which way it's going to shift. Okay? All right. Any other questions? Once? Twice? Sold.